Okay, this is the beginning of part 2 of the extra review for the final. One of the things, as we've always talked about, is sometimes you need to find the equation of the tangent line to a graph at a given point, x1, y1. What you need to do is first find the first derivative of the function and find out what its value is at the point x1. That will be the slope of the tangent line at the point. Then you write down y1 equal mx1 plus b and solve for b. Then the equation will be y equal mx plus b. So for instance, let's find the equation of the tangent line for the function f of x equal x minus x squared. Y prime, of course, is equal to 1 minus 2x. And so y prime at x equal 4 is just simply 1 minus 2 times 4 equal minus 7. So this is equal to m, the slope of the tangent line. So we can write down that the equation of the tangent line is y equal minus 7x plus b. And we want to plug in the point 4 and minus 12 to find b. So plugging this in, we get minus 12 equal minus 7 times 4 plus b. And so you get that b is equal to minus 12 plus 28 equals 16. So the equation of the tangent line is simply y equal minus 7x plus 16. Now why don't you pause the video in a second and work the second example, and then take a look and see if you did it correctly. Now, to do this problem, we need to write down that y is equal to 10x to the 1/2 minus x plus 1, and that y prime, the first derivative, it then would be 5x to the minus 1/2 minus 1 equals 5 over the square root of x minus 1. And we want to calculate y prime at x1, which is 100 in this case. So that would be 5 over the square root of 100 minus 1 equal 5 over 10 minus 1, which of course is 1/2 minus 1 equal minus 1/2. So the slope of the tangent line is equal to minus 1/2. So now we know that the equation of the tangent line is y equal minus 1/2 x plus b, and now we need to plug in 101 as a point. So y is 1 minus 1/2 times 100 plus b. Solving for b, you get b is equal to 1 plus 50 equals 51. And then y is equal to minus 1/2 x plus 51. Now the next problem is finding limits. We know we talked about several ways to do it. If you can plug in the value that x is approaching and calculate a value without getting like dividing by 0 or 0 over 0. That's it. That works for most functions. You can also try your calculator and put in a value of x very close to the value that x is approaching, and that will, if you have a calculator with a lot of decimal places or calculating capability, that would do. You could also sometimes factor and then factor out the problem factor that's going to 0, or you could just use what we call a trick or another strategy. What I'm going to show you here, and the other possibility is to use L'Hopital's rule. For this first problem, I'm going to use L'Hopital's rule, and if you plug in x equal minus 1, you get 1 minus 1 equals 0 over the square root of 4 minus 2, which is also equals 0. So you get 0 over 0, so you can use L'Hopital's rule, which means you can take the derivative of the top and the derivative of the bottom and then plug in. Well, the derivative of the numerator is 2x. The derivative of the denominator, we would have to write this as x squared plus 3 to the 1/2 power minus 2, and then take the derivative, and you can see that would be 1/2 x squared plus 3 to the minus 1/2 power times, remembering the chain rule, times 2x. Notice that this is equal to 2x within in the denominator 1/2 1 over the square root of x squared plus 3 times 2x. And notice all of a sudden we get 2x and 2x to cancel, dividing through by 1 over 2 times the square root of x squared plus 3. We get 2 times the square root of x squared plus 3, and plug in x equal minus 1, and we get 2 times the square root of 4, and that of course is equal to 4. So the limit is 4 using L'Hopital's rule. What I will also show you is what you get if you use the trick. Give me a second to erase some of this. What we would do is multiply by the radical plus 2. But let's go ahead and write down the square root of x squared plus 3 minus 2 times the square root of x squared plus 3 plus 2, and then multiply the numerator by the same radical plus 2. And when we do this, we get x squared minus 1, the radical radical x squared of x squared plus 3 plus 2. And then the denominator is going to get very simplified. Multiplying the radical of x squared plus 3 times the radical of x squared plus 3, we get x squared plus 3. And then the outside terms is plus 2 times the radical. The inside is minus 2 times the radical, so they cancel, and then you get simply minus 4. So notice this denominator becomes x squared plus 3 minus 4, which is equal to x squared minus 1. Notice that that cancels with the numerator, and then all we have to do is plug in x equal to minus 1, and we get the square root of minus 1 squared plus 3 plus 2, which is 4. Now why don't you pause the video and look at the next problem and see if you can work this one. In fact, why don't you try using L'Hopital's rule. Okay, if you just plug in x equals 0, you can see at the top we get, in the numerator we get the square root of 36 minus the square root of 36 over 0 equals 0 over 0, which means we can use L'Hopital's rule. Notice we take the derivative of the numerator and we take the derivative 36 plus x to the 1/2 power. That derivative is simply 1/2 36 plus x to the minus 1/2 power minus the 36 minus x to the minus 1/2 power. Now you have the two minuses because when you take the derivative of 36 minus x, you get of course you have a 1/2 here also. You have to take the derivative of the u, which is minus 1. That's why you have a minus 1 here. So what you now have is 2 of these at the top, and the derivative of the denominator is 1. So we get 1 over the square root of 36 plus x and plugging in x equals 0, we get 1 over the square root of 36 equal 1/6. Now another problem that we have to do is finding maximum and minimum. As you know, what you first do is you calculate the critical points, that is where the first derivative is equal to 0 or undefined. You can then determine the concavity at the critical points. And of course, if the second derivative is more than 0, it's concave up, and it's a relative min. If the second derivative is less than 0, it's concave down, and it's a relative max. If you are asked to do this over an interval, you also have to check the value of the function at the endpoints. So the particular problem we have here is f of x equals 7x over x squared plus 1. We need to take the first derivative, and the first derivative of x, function of x, is equal to x squared plus 1 times the derivative of the numerator, which is 7, minus the top 7x times the derivative of the denominator, which is 2x, divided by the denominator squared. Simplifying this, you get 7x squared plus 7 minus 14x squared over x squared plus 1 squared, and that is equal to minus 7x squared plus 7 over x squared plus 1 squared. We set that equal to 0, and this can only be 0 if minus 7x squared plus 7 equals 0, or x squared equal 1, or x is equal to plus or minus 1. So we need to check the value of the second derivative at x equal plus or minus 1 to see whether it's concave up or concave down. So now we take the second derivative, and looking at this function, taking the first derivative of the first derivative is the second derivative, we get the bottom, which is x squared plus 1 squared, times the derivative of the top, which is minus 14x, minus the top, which is minus 7x squared plus 7, times the derivative of the denominator, which is 2, times x squared plus 1, times 2x, remembering the chain rule, all divided by x squared plus 1 quantity to the fourth power. Now, simplifying this, notice that we can factor out an x squared plus 1 in the term in the numerator. So doing that, we get x squared plus 1 times x squared plus 1 times minus 14x, and what is left here is if we take a minus out of the minus 7x squared plus 7, we get minus 7x squared minus 7. And so this becomes a plus, so we can get a plus this 2 times the 2x, which gives you 4x. Notice we've already taken an x squared plus 1 out, and so we're just left with 7x squared minus 7. divided by x squared plus 1 to the fourth power. Now, multiplying this out, we get x squared plus 1, which of course is always going to be positive, x squared plus 1 to the fourth power in the denominator. And what is going to determine the sign of the second derivative is this term, which we need to multiply out, which is going to be minus 14x cubed minus 14x plus 28x cubed minus 28x. And so we get x squared plus 1 times (14x cubed) minus 42x all over x squared plus 1 to the fourth power. Now, evaluating this at x equal 1, we get that this term is less than 0. Plugging in 1 here, so that it is concave down, which means it's a relative max. And plugging in x equal minus 1, we see that that term is going to be minus 14 plus 42 is more than 0, so it's concave up. That means it's a relative minimum. And so if you plug in x equal 1 in the function, you get 7/2, which is a relative maximum. Plug in minus 1 into the function. It is a relative minimum, and the value is minus 7/2. Now, why don't you try this second one. Pause the video now. This is a little bit easier than the previous one. Calculate the critical points and see if you can find out which points are relative min or relative max. Okay, the first derivative of x is minus 3x squared plus 6x. We set it equal to 0, and we factor out a 3x and get minus x plus 2 equals 0. So we get x equals 0 and x equal 2 are the critical points. Calculating the second derivative of x, we get minus 6x plus 6. The second derivative at 0, which is the first critical point, is equal to 6, so it's concave up. So it's a relative min. Plugging in x equals 0, you get y equal minus 2. So we determined that point 0 and minus 2 is a relative min. And now let's check the second derivative at 2. We get minus 12 plus 6 is less than 0, so it's concave down. So x equal 2 is a relative max. Plug in x equal 2, you get y equal 2. So the relative maximum is x equal 2, y equal 2. Problem 12, still looking at maxima and minima, but this time we're going to look at the function over an interval from minus 1 to 3. So now we have to look at not only the points where the derivative is 0, but also where the endpoints are. So first of all, calculating the critical points, we get f prime of x is equal to 3x squared minus 3. Set it equal to 0. We get 3 times x squared minus 1 equals 0. So x equal minus 1, x equal plus 1 are the critical points. So we need to check the function at minus 1, plugging in minus 1 to see what the y value is. We get minus 1 cubed minus 3 times minus 1 plus 5 is equal to minus 1 plus 3 plus 5 equals 7. Let's check F at plus 1. And of course we get 1 minus 3 plus 5 equal 3. And endpoints. We've already checked minus 1, which is one of the endpoints. So let's check x equal plus 3. Plug in plus 3 and we get f of 3 is equal to 27 minus 9 plus 5 equal 23. Now we look at all of these values, and of course the other endpoint happens to be minus 1, so we calculated it too. So the absolute max is 23. And the absolute minimum is equal to 3. Now looking number 13 here, remembering the fundamental theorem of calculus, it says if you have capital F of x is equal to integral from a to x of f of t dt, then the derivative, all you have to do is plug the x in everywhere you see a t. However, remember, if the upper limit is a function, then you have to plug in g of x everywhere you see a t and then take the derivative of the upper limit. That's the chain rule. So in this first example, the derivative of the integral from 0 to x of 7t cosine of t to the 6 dt. It's just going to be plugging in x everywhere you see a t, and you get 7x cosine of x to the 6. However, if you have a function like the second one, in which you're taking d dx of the integral from 0 to sine of x, notice that sine of x is not just plain old x, so now we have to plug sine of x everywhere we see a t, and so we get 1 minus sine square x in the denominator, but then we have to take d dx of sine of x, which is cosine of x, and multiply that times the result. Now, the other fundamental theorem of calculus, which your book calls Part 2 and I like to call Part 1, which is probably the most important one, fundamental theorem, simply says that if you have a function f of x and you know its antiderivative on the interval from a to b, that the integral of the function is just the antiderivative evaluated at b minus the integral of the function, and I just noticed an error here, evaluated at a. So it's f of b minus f of a. And as you know, we sometimes write this as f of x from a to b, which means you put b in first and then put a in and subtract it from f of b. And this is what we use to calculate the area under curves and calculate definite integrals. Now we have an optimization problem here. Now you have seen us do a similar problem like this. We have a sheet of metal 12 inches by 10 inches long. We're going to make an open box by cutting out x in each corner. We're going to cut out these square corners. Each piece will have a length of x, and then we're going to fold up and create a box. And the idea is to get a box with maximum volume. Notice that the length of the box is now going to be 12 minus 2x, and the width of the box is going to be 10 minus 2x, and the height of the box is going to be x. So the volume is going to be x times 10 minus 2x times 12 minus 2x, which is equal to x times 120 minus 24x minus 20x plus 4x squared. And after you multiply all this out, you get 120x minus 44x squared plus 4x cubed is the volume. Now, To find the value of x that maximizes the volume, we take v prime is 120 minus 88x By the way, this is 4x cubed. So the derivative of that is 12x squared. And set it equal to 0. And factoring a 4 out, we get 4 times 30 minus 22x plus 3x squared equals 0. This is a quadratic which you can solve with the quadratic equation and get that x equals 22 plus or minus the square root of b squared, which is minus 22 squared, minus 4ac, which is minus 4 times 3 times 30, all over 2a, which is 6. Putting this in your calculator, you get x equal 1.81 and x equal 5.52. We would reject the 5.52 because if you took that out of a side with just 10x in the length, it'd have no box. So the correct answer is x equal 1.81. And so the height of the box is going to be 1.81, and the length of the box is going to be 12 minus 2 times 1.81, which is equal to 8.38. The length of the box and the width of the box is going to be 10 minus 2 times 1.81, which is 6.38. Notice that you can also put this function in your calculator and very easily see that x is 1.81. One of the problems that we looked at is what we call related rates, which is mainly a problem in which something is changing that affects something else, and you want to know how much the overall thing is changing when something else is changing at a certain rate. So here water is falling on a surface, wetting a circular area that is expanding at a rate of 9 square millimeters per second. How fast is the radius of the wetted area expanding when the radius is 166 millimeters? So we have a circular area formed by this water falling on a surface, and its radius is r. The area of the wetted area is equal to pi r squared, and we know that area is changing at the rate of 9 square millimeters per second, and we want to know what dr dt is. So to do this, we look at the area equation and take dA dt. That is equal to 2 pi r, which is the derivative with respect to r, but you have to multiply times dr dt, which is the chain rule. Now, plugging into this, we know that dA dt is 9. We want to find out dr dt when the radius is 166 millimeters. So dr dt times 2 pi times 166 is 9. So dr dt is equal to 9 over 2 pi times 166, which happens to be 0.0086 millimeters per second. Now, why don't you pause this and look at this second problem. We can talk about it for a second, then you try to work it and pause the video. Water is discharged from a pipeline at a velocity v given by v equal 1064 times p to the 1/2 power, where p is the pressure and psi. If the water pressure is changing at a rate of 0.266 psi per second, find the acceleration dv dt of the water when the pressure is 32 psi. Well, it says the velocity of the water is 1064 times p to the 1/2. We want to find dv dt, which is dv dt equal ddt of 1064 p to the 1/2, which is equal to 532 p to the minus 1/2 times dp dt. In other words, we're taking the derivative of, with respect to t, of this function, and all we see is a p. So we take the derivative with respect to p and then multiply by dp dt. Now we've got dv dt is equal to 532 square roots of p times dp dt. Now we calculate dv dt as we want to do it when the pressure is 32, so we take the square root of 32, and it said that dp dt is 0.266. So multiplying this out, we get 25.01 is dv dt. Now, I want you to look at this particular note on the fundamental theorem of calculus, part 1. And here we're given the function y equal f of x. And I've drawn this function, and at various points I have indicated exactly how much area is there beneath the curve. What we want to do is to find the function s of t equal the integral from 0 to t of f of x dx. That means that if we pick a given t, like t equal 2, we want to know how much area is there at t equal 2. Well, looking at the function, you can see that that answer is 3 plus 8 is the total amount of area you have from 0 to t equal 2. So what I want you to do is fill in this table here for various values of t and observe what is happening to s of t for various values of the t. So let's look at it. Obviously at t equals 0 you picked up 0 area. At t equal 1 you picked up 3. At t equal 2 you picked up 8 more, so you have an area of 11. At t equals 3 you picked up 9 more, so you have s of t is 20. At t equal 4 you picked up 6 more, and you have 26. At t equal 5 you picked up 2 more, and you've got 28. Now notice what happens here. The minute the function goes below the x-axis, any area is counted as negative and it subtracts from the value of the function. So the area or the integral from 0 to 6, we would subtract 2 off. And so at t equals 6, we would have 26. Notice that now s of t, it increased all the way up to t equal 5 and begins to decrease when the function goes below the x-axis. Now, if we go to t equal to 7, we subtract another 5 and we get 21. If we go to t equal 8, we subtract another 2 and we got 19. So now we've gotten to t equal to 8 and the value of the function is 19, and it's lost all it's going to lose, because now when we get to t equal 9, we've added 3 more. So that's 22, and then we add 8, gives us 30. Then we add 9, gives us 39. Then we add 6, gives us 45. And add the last 2, and we get 47. Now, I want you to look at the next page and graph s of t, and you'll be answering some questions. One thing you should realize that as long as you're picking up area, the function is increasing. The minute the function goes below the x-axis, you begin to lose the value of the integral, and it keeps on decreasing as long as the function is below the x-axis. So let's look and graph the function on the next page. If you graph it, you get at t equal 1, you get 3. T equal 2, you get 11. T equal 3, you get 20. T equal 4, you get 26. T equal 5, you get 28. T equals 6, you get 26. t equals 7, you get 21. T equal 8, you get 19. T equal 9, you get 22. T equal 10, you're back up to 30. T equal 11, you're up to 39. Just doing this roughly. T equal 12, you're up to 45. T equal 13, you're up to 47. And here roughly you have the value of S of t. Which I roughly graphed here. Now, the question is, what is S prime of t? And we already know from the fundamental theorem of calculus that that's just simply f of t. And S double prime of t would be f prime of t. And one question, at what value of t does f reach the first relative max? It turns out it happens to be at t equal to 5. And you can see why that is, because at t equal 5, when we integrated all the way to 5, it had picked up the most it was going to get, and then it started decreasing. And then the other question, at what value of t does it reach its first relative min? And that is at t equal to 8. And that is simply because at t equal 8, we have subtracted off all we're going to from the integral, and we begin to increase again. So you can see here we had our first relative max at 5 and the first relative min at 8. And you can do this by just calculating the value of the integral.